Yes. Thank you. Thank you for inviting me. I moved to the UK quite recently, so it's my first time in Oxford. Thank you for having me here today. So today I want to talk about this recent project on how we can coarse a spatial graph using some topological data analysis. So spatial graphs are graphs where the nodes are embedded in space that you can call M, but in this talk it's going to be an Euclidean space of dimension either 2 or 3. So these data are very interesting, I think, because they arise naturally as a way of describing many applications. So for example, here just to give you some examples, this is are the ductal tubes, which are little tubes that develop within the pancreas. So they have a tubular structure that, if skeletonized, can be naturally described as a spatial graph. So the graph with nodes embedded in R3 in this case. Another example, this is the data that I'm going to describe today in more details, are the network that the fungus built to reach for nutrients, which are called mycelia network. And these networks, they are almost like a 2D network, so they develop flat, almost flatly. This again is an example of spatial network. The third type of data that can be represented or modeled as spatial graphs are, for example, very porous and irregular tissue. Like, for example, this is a cardiac fibrotic tissue that if you skeletonize it, you can describe it as a spatial graph structure. And the last example are, for example, transport networks. Okay? So this type of data arises in many different types of applications. So my research focused on how to define methods for a population of graphs. So this has been my research for some years now. And I worked mostly on graphs, which are abstract graphs up to node permutation. And I started working on spatial graphs quite recently. But for the other type of graphs, we developed many different statistical tools, like, for example, regression, principal component, uncertainty quantification, and so on and so forth. And recently, we started working on how to develop methods for a population of graphs that has also a spatial component. So today I want to focus on dimensionality reduction, which is one of the aspects you can look at when you have a set of spatial graphs. So this type of data, like the one I described before, they usually are very big in dimensions. They have a lot of nodes, a lot of edges, and they're very big. So the goal is to try to define a dimensionality reduction procedure. So to basically decrease the number of nodes and edges, retaining the most important topological information of the graph you're observing. Because the idea is that we are looking at this data a bit like a shape data. So we have some sort of shape structure, a topology that we want to retain when we decrease the dimension of the graph. So interrupt me if you have any questions. So what I'll do today, I'll start by defining spatial graph and spatial graph coarsening. Then I'll describe how you can characterize the topology of a spatial graph. This has been done a little bit in the literature. And then I'll put the two things together and define a topological spatial graph coarsening procedure. And then I'll study a bit the property of the spatial coarsening because we want the method to be invariant under certain group action that makes sense for this object. And this is a joint work with Etienne Lassalle, who is the, let's say, the topological data analysis expert in this work, and is on ARC. So let's start with defining the object of the analysis and the coarsening procedure for this spatial. So what is a spatial graph? Spatial graph can be defined as a set of vertices and a set of edges, which represents the connectivity point. Then we're gonna equip it with the X, which are the set of coordinates, for example, in R2 or R3. You can also embed this graph in a manifold structure, like on a sphere or something. But for this talk, we're just gonna focus on an Euclidean embedding of the nodes. And then you have dv, which is a function that is a distance between the vertices. Okay, it can be the geodesic distance, but can also include some weights on the edges. So it's a metric function on the graph. So this is the object of analysis. So here you have a simple example where you have the nodes embedded. I'm sure you're familiar with this. So what do we want to do? We want to do dimensionality reduction that in this case is actually a coarsening procedure. So we want to take this graph, for example, the one here, and return a graph that has a lower number of nodes. and consequently a lower number of edges. So how can we define a coarsening procedure? First, this coarsening procedure is defined at the given scale theta, and this is going to be an important parameter. And once I have this parameter theta, this function f of theta is going to be applied to the vertices, the edges, the coordinates, and we leave the dv function unchanged. So we're going to just drop the distance function for because we don't. So what do we need? We need a first component which acts on the node. So the coarsening is grouping the nodes into a hypernode. So we're going to select a specific element of the partition of the original node of the graph, like you see here. So, oops. Yeah. So basically, we're grouping, for example, the nodes such that the distance defined on the graph is smaller than a given scale theta. Okay, this is classical coarsening. And this is going to return a new set of nodes that are a group of the original, a partition of the original node set. The second part is the edge. So the edges are going to be updated, and I'm going to add an edge between the hypernodes if there were at least one edge in the original graph. The other component of this function is updating the position of the nodes in the graph. So there are different ways you can update the position of the node once you have a coarsening structure. One way is to use what we call an average positioning, which is simply assigning to the node the average position of the nodes in the original graph. So you can just pick the average. The other strategy is to use what we can call degree positioning, which basically means that we're picking one of the original nodes and the one that has higher degree. One of the one that has higher degree can have more than one node with the same degree. So there is not a good or a bad choice between the degree position and the average position. Really depends on the application. Let me give you these two examples. So suppose you have a road network. For example, this is Marseille in south of France, and you have the network of the road in the city. And you want to coarsen this graph with the procedure that I'm going to describe later on. When you coarsen the graph, you don't want to use the average position. You don't want to just put the nodes in an average position that doesn't really exist in space. You're going to keep one of the original nodes when you coarsen your graph. And if you use the degree positioning, it will be the node with a higher number of branching streams. So this is a good choice when you work with this type of nodes. If you're working with this type of object, which can also be called shape graphs, so a skeleton of a shape, for example, the tubular structure I was showing you before, then here we're describing a shape. So the positioning of the node comes out of a preprocessing, which is a skeletonization procedure. So we can use the average to kind of keep track of where the new nodes are. Okay. Do you have any question about this? Now, what we want to do is to do this coarsening procedure, taking into account the topological property of the original graph. So the whole point is to select a scale that is meaningful, that in a way balance between reducing the graph and retaining the important topological aspect of the graph. Now, this is what I just mentioned. So if you have an original graph and you have the procedure that I described before, the question is, how can I pick the theta such that I can preserve some principal topological features of my original graph? So for example, in this analogous example, what you can see is that one of the most important, or the principal, let's call it topological feature, is actually this central hole. So you can go all the way down to here, but probably it's better to stop at the point where I'm getting rid of the noise around the hole, but I'm able to keep the shape, the main feature of the shape. So that's the idea. So the question is, how can I characterize the graph with the tools from topological data? So how can I characterize this principal topological feature of it? So I'm not an expert of TDA, but I don't know if you're familiar with the topological data analysis tools like persistent diagrams or, yeah, that's even better. Perfect. So basically, this is like a very quick introduction, but basically topological data analysis has been, receiving a lot of attention in the past year in both the stats community and the kind of machine learning community, because it's a tool that can be used to describe the topological structure of, for example, a point cloud. So there are many tools. One of the most famous one, let's say, is what is called a persistent diagram, which is a tool to describe basically topological characteristics of point cloud, for example, or even a graph. So if you're familiar with the persistent diagrams, these slides are a bit useless, but the main idea is that you're going to build a filtration around the point cloud. That is, for example, one of the famous one is what is called victorious leap filtration. And this filtration, which is you can see this filtration is built by drawing topological balls around your points, and you're saving in these persistent diagrams the point into which a component born and is born and is that. Okay, so if you're familiar with the persistent diagram, this is just simple introduction. So for example, let's go at the very end. If I draw. So for example, given this very simple point cloud, you will have these 1, 2, 3, 4 edges, and then one higher order interaction, which is the simplex basis that you can see in here. Okay, so you can turn your point cloud in this case into a set of points in R2, which are birth and death. So they are all in the upper part of the diagram. Now, the question is, what if I start with a graph? So how can I extend the persistent diagram for a graph object? And there's been different attempts in the literature to do that. So the basic idea is that I need to build a topology that accounts for the structure of the graph. So I don't have points that lives in R2, for example. I just have nodes that lives on a graph structure. So I need to study topology rooted on the graph structure. So the main idea is to change the way I build my filtrations. So as I said, some attempt has been done in the literature to extend the classic filtration to graph data. The whole idea is to find a way to group those nodes. So you can use many different statistics on the graph to actually group the nodes, increasing a given scale on a function you choose. Can be the node degree, the Jaccard index, the it kernel, the Ricci curve. So you can think of all sorts of things. What we decided to do, sorry, this is going, yeah. What we decided to do was to build a filtration that is based on this is kind of an intuitive idea, is to use the distance defined on the graph itself. So we're going to build the filtration using dv, which is the function I defined at the very beginning, which can be a geodesic distance between the nodes, for example. So I built a filtration based on this geodesic distance, and now I have the same filtration I had before. So I have a filtration defined on the graph, and I can build a persistent diagram out of it. There is an additional trick that needs to be done, and this is for having two simplets to appear at a certain scale. This is basically a trick to avoid having these points literally being on the diagram. So I want them to basically be born a bit later in order to actually see them appear in the persistent diagram at a certain scale. So why this is needed, let me go, I have time so I can do that. I'm just gonna go 1 second at the very end. Yeah, so this is the trick we need to do. So if you suppose you have this simple graph structure, this is the dv function. Okay, so 3, 4, 5 are the value that this function takes. If you build a filtration, normal filtration, you will see that as soon as the third edge appears into a triangle, it will kind of directly count as an higher order interaction. What we want to do is to be able to see this in the persistent diagram. So we trick it by making it appears at the scale equals 7. So that's just a trick to actually see this higher order interaction in the filtration. It's kind of a technical trick. So let's go back over. Okay, so long story short, we are defining a persistent diagram for this object. So what does it mean? It means that now if we have a graph like the one I was showing you before, we're able to build a persistent diagram to describe the topological features of this graph. So if you, for example, look at this original graph and the persistent diagrams, what do we see here? So we see all the edges, which are these red points. And then we see here around the diagonal, all these little higher order interaction, like cycles that appears, you know, here, 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 here. And then you see up here, this bigger cycle, okay? So the idea is to try to find a scale for our coarsening procedure that takes into account this topological information. Okay? You have a question? No.
That's a great question.
Yeah, you go ahead.
So at the start, you spoke about the two different methods of positioning the nodes, the like average and
yes.
degree. Is there like in those results, are there differences choosing one method or the other?
No.
Because they're all pretty much the same.
Yes, because the coarsening procedure is based on the topology, on the structure of the graph. What that part is doing is updating them on this, okay? But it somehow doesn't change the DV function.
Do you tend to use one approach or the other?
Yeah, I think it really depends on your data. If you have a shape where the scale, if you have a skeletonization procedure, there is a variability around, an uncertainty around where to put your nodes. So somehow you can use the average to smooth it out, yeah. But if you have a road network, I think that's a perfect example where it doesn't make sense to use the average because you will put a road cross in a place that doesn't really exist. So I think really depends on the data you're looking. And there might be other options that we haven't explored, no other way of updating.
Why is there one plus?
Because this is when you have only one connected component where they are all grouped into one. So you can grow your radius as much as you want, nothing else is in this. Okay. Okay, now let's, we talked about spatial graph coarsening. We talked a bit about how to build the persistent diagram. Now let's put them all together. So, as I said, the idea is to account for the persistent diagram to find an optimal scale for reducing the graph. Like we have an original graph, a reduced graph at the given scale, and we want to obtain this reduced graph by also accounting for the distance between the two persistent diagrams. I don't want to have a scale where, for example, I'm cutting this cycle. That's the one. So the idea was to define a score function and this score function. So you have a starting graph, a coursed graph. You have the two corresponding persistent diagrams. So the score function is based on, has two different components. One component is accounting for the number of edges that I'm deleting when I'm coarsening. So how much edge I'm getting rid of. And the other component is a distance function between persistent diagrams. Okay? So what I want is a trade-off between getting rid of many edges because I want to simplify the graph, that's the final objective, and also preserving the topological structure. So there are different distances between persistent diagrams. The most famous one, let's say, is the so-called bottleneck distance, which is a distance that basically given two persistent diagrams, which are just two point clouds in two, matches those points. And if we have more components in one than the other, it will match to the diagram. So it's kind of a Wasserstein type of distance where I also include the diagram for accounting for unbalanced number of points in the two persistent diagrams. Very kind of standard metric between persistent diagrams. So let me add one more thing. So this score function is just one option. There are many other ways you can account for the topological characteristics of the graph. So you can also build you can change this part and include in this component another way to compare the graph topology. Okay, so you can say, I don't want to get through all this fancy TDA stuff. I can just do, I count the number of cycles. And you can just plug there a different type of metric. Okay. The reason why we started with persistent diagrams is because they have a kind of a very big full picture, and they are intrinsically based on the concept of scale. So that's why we wanted to look at that. So you have the scale of the coarsening and the scale of the filtration. So they work nicely together in this conception. But you can implement either version where you have another type of indicators here to build the score function. Okay, so then what are we doing? We have an original graph, a reduced graph. This reduced graph is found by finding this optimal point theta. In blue, you have the score function. And then you have, that is the linear combination of these two components. So the number of edges, which of course decrease when you increase the scale because you're grouping everything into another node at the very last, in the extreme Coarsening graph. And the other component are the distance between the persistent diagrams, which of course increases.
I didn't quite catch how you find the optimal threshold theta.
So the theta is the minimum of this function that usually have this kind of the blue. Then you have a range into which you have a plateau usually. So this is a bit of a trick to choose. Either you can also stay here potentially. So you can pick a value within this minimum range. Other questions? No. Okay.
Can you go ahead? Is it the choice of beta as like the most right point on that kind of plateau? Is that deliberate, or is like I'd say minimum in this?
Yeah. Yes, we wanted to. If you travel there, it's a trade-off between the two elements. Okay, so if you pick this point, so if you pick when it starts increasing, you're basically trying to avoid being to getting too far, topologically speaking. You see the green curve. So if you are here, then you are obtaining a graph that is very far topologically. But you can also stick to a point here. Let's say that I think one of the points we didn't explore well enough is exactly this, like how to properly optimize it. Okay, now let's spend a few minutes on the property of this procedure. So when you work with this spatial graph, especially from the one that comes out of images, like for example, a skeleton of a tubular structure, you usually want to work them up to rotating, scaling, and translating, because they are seen as a shape. So I want to study this despite how it's presented to me. That's the idea. So we spent some time exploring the property of this procedure with respect to this specific group action. So first, let's see how the similarity group act on this spatial graph. So if you have an original graph G, you can define a map psi that takes a graph and an element of the similarity group, and it will act on it will leave the vertices and the edges untouched because these are just representing the structure, the graph structure, and then it will act on the node position, okay? And you can have a K, which is a scaling parameter, an R, which is a rotation, an orthogonal matrix that describes the rotation, and then you can also translate it, okay? So this is just how I can take a G and apply the group action to this graph. So the nice thing is that this topological spatial graph coarsening is what is called parameter equivariant under the similarity group action. So I think it's much easier to look at this like this. So if you start with the graph G, and then you apply your coarsening procedure to the graph G at the given scale theta, and again, this theta parameter, thanks to this Fourier function, is kind of automatically computed. So I apply my methods, I have an optimal theta, and I coarsen my graph. I obtain a coursed graph at theta of G. If I receive the same graph that under this group action, so has been, for example, rotated or scaled at the given K, then I'll obtain exactly the same graph where the parameter has been scaled, okay? This is, seems, it took, I mean, it's not difficult at all conceptually, but then it took quite some time to formalize it properly. But the idea is basically, if you give me the same graph, rotated, translated, and scaled, I'll get you out the same coarse graph at a different scale that has been just applied with the same scale multiplied by this parameter, which is the same I have in the group function. It's the same element of the group function, I'm not planning to. So it's nice to have this property because this is really a problem you have when you work on React. You can really receive them up to these group functions. Okay. So, and that's exactly what I'm saying. So if I have a G and a new G that has been rotated and blah, blah, I'll get exactly the same structure out with the corresponding rotated result. Okay. Okay. So let me describe this collaboration that we have with a group here in Oxford of biologists, where we studied a data set of fungi, and we applied this coarsening procedure to this. So the data are like this. So they are looking at how a fungus implanted in a wooden block will grow this mycelia network, which are literally a network of roots that the fungus have to reach for nutrients in the soil. So they are interested in studying this for many different reasons. They are interested in understanding different species and what is the network of these different species. Or they're also interested in understanding when you have some attacks from the outside, like little animals eating the network, how the network changes. So to study somehow how resilient this network is with respect to external agents. So these are the original images, and then what we have are graphs extracted from these original images through a skeletalization procedure. And these data are generated by Mark Fricker here in Oxford. So how the data looks like? There are 128 graphs of 3 different fungus species. As edge weights, they have a resistance parameter. So this is also important to mention that you can encode weights on your graph and basically account for those weights when you build the persistent diagram. So somehow take those into account when you do the percentage procedure. So the node attributes are 2D spatial nodes. This is beautiful because these are, you can consider them almost as 2D for real. So you can really forget about the width of this because they're almost flat. And then we have 3 types of grazers, which are animals attacking the network. And there is 2. One is no grazers, so it's a control group. Then you have small grazers and large grazers, which are more than 10 millimeters. For example, worms. The large one are worms, the other are very little animals that can attack the network. So the final objective was to build a classifier to predict when you see a graph structure if it has been attacked to by certain type of grazers, like if it was in the control group or if it was attacked by a small or a large. So the idea was, can we perform a dimensionality reduction procedure on the data set because the data are very, very big, like almost intractable big, and it's basically a way to check the quality of the coarsening procedure to build the classifier on the original and on the reduced data set and see if the performances were different. It's kind of a test. We thought it was a way to test if we are retrieving important information when we are coarsening the graph. That was the idea. So first, let's look at the dimensionality reduction. So you have the box plot of the size of the original graph set, and then you have the reduced one. So you can see that we have been reducing the data set. And this plot is also interesting because here we are trying to understand if we are always picking the same data that corresponds to the same quantile of the width in every graph. So we were interested in understanding if we were always chopping in the same way somehow. And this is not what is happening, and you can see it through this histogram. So basically, we pick is a way of saying that you pick the right theta for each one of the graphs. You can actually see that you are tuning your parameter per graph well, and not just chopping always at the same in the same at the same scale. Okay. So, for example, these are 3 examples of 3 different graphs from the 3 different groups. This is an original graph, and this is a reduced graph for the control group. And again, here, just to come back to what you say, like, for example, here we're picking these points. So in practical implementation, there is a Python package for this. We just sample in the scale some points, and then we pick the minimum. Like, this can really be improved. Here is another example of the original graph and the reduced graph for for the Cebola grazers, which are the small grazers. And here is one that has been attacked by very big grazers, okay, so big worms. So, and you can see, I like this visualization because I think you can see that in this graph, you also have this fictional wooden block. So it's nice that, you are able to kind of always keep this information, and plus you are reducing the graph in a way that you have a less number of nodes, but still keeping, information about the structure. And if we look at the performance of a classifier, so here we just use the random forest classifier, but you can use a fancier method. This is just a proof of concept to see that we are, of course, not performing as well as when we work with the full data set, but we are still performing in the range.
So can you go back to the
Yeah.
Because the effects data seems to be not volatile and it goes down again. But how do you know that it wouldn't have another millimeter?
This one here.
Good one.
Yeah. So here I think it's because there might be an effect on this ratio. Let me think. Or is about the bottleneck. So this is decreasing, okay, and this you have an effect of these components that is going down again. Yeah. It could be when you. That's a good point. So you're asking what can happen here.
I think the score function should go down.
Yeah, that's what it should do. But here is jumping a little. Yeah. So all the cases we observe is actually having this type of shape, but it's true that it can go down as well. But we never observe equally good minima. I think it's because you might have points. So this is an optimized function because it's a matching function. So you might have some error coming from the way you compute the bottleneck distance. Can be. I don't know. That's the point. Yeah. Thanks. I'll look a bit more into this. Yeah, so this is just, these data are very rich. There are different things you can do, but this was just a way to kind of play a little bit with this coarsening procedure as a pre-processing step, let's say, for another task like classification. So, yeah, I think, as I said, it was quite a short talk. So today I wanted to talk about this project with Etienne, where we defined this coarsening procedure for spatial graph. So I introduced the procedure, how you can compute the persistent diagram for a spatial graph, and I described the property of these coarsening methods. So there are different future extensions. One, which is related to the question you mentioned, is to work a little bit better on how to find this optimal minima and also the property of the score function. The other extension, which goes a bit more in the direction of the majority of the research I do, is to try to build this coarsening procedure, but accounting for the population. So this coarsening procedure is now defined per graph, but I think it would be very interesting to start looking at the population, because the population have a variability that you might want to account when you do this dimensionality reduction. So that's what I would like to do next. So to move more towards a population approach of the same coarsening procedure, and I think that's a further future extension of this work that I presented. But what I want to say, in more concluding with a more general thinking, is that I think these spatial graphs are really everywhere. So there are many, many different data types that can be described thanks to skeletonization procedure, or just naturally as they are kind of defined and constructed. that can be studied as a spatial graph. And these objects are really in between abstract network analysis and shape graphs. So there is really a room for a methodological development of tools for these data objects, because you really need to kind of borrow from both shape analysis and network analysis. So we're working on many different projects to develop tools for these data, specifically for this data object. In particular, there is one project in collaboration with colleagues in Denmark where we study the pancreas. So these are the ductal tubes in the pancreas. So we have microscopic images of how these tubes develops in an embryo. And the question here is to study the data with a longitudinal data analysis approach, because we are measuring how the structure grows in time. So here you have a lot of questions like, how can I actually build a time series? How can I study a time series of these spatial graphs where I have, and this is a bit related to what we were discussing before, I have information that travels on the graph. I also have the shape of the graph that changes. I have a problem of alignment because they usually come from different mouses. So I have all these type of problems to address. Then we have this collaboration with the Mark here, where we have this data. These are very rich data, and they are interested in all sorts of different things. For example, testing procedure to understand if the species developed in a different way, and so on and so forth. And this data has been mostly studied using standard network analysis tools. They can be looked at. Them as a spatial graph. And the other type of data, which I described at the beginning, are these very porous structures. So these are cardiac tissue in the heart, and there again, if you study them as shape, you can't find anything interesting. Like, it's very hard because you don't know where to put the landmarks, and standard shape analysis doesn't really work for these objects, right? So it might be useful to kind of look at them again as a network, because you can better study all this kind of porous structure and fragmented perimeter in a better way. Yeah. So this is the first graph ever, which was a spatial graph, right? Because it's the bridges. And yeah, here are some references, and I think that's all for today. Thank you.
Any questions? Can I just ask how you chose the alpha? Because there was also an alpha parameter which is essentially a regular.
Yeah, good question. It's we picked it as a ratio of I don't remember, but yeah.
So that could change whether maybe.
Yeah. We needed to make the quantity compact.
Yeah, that's good. Question.
Go ahead.
So for each reduced graph, we set a parameter sigma. Yeah, it corresponds to a point in a resistant diagonal space.
Yes, is this exactly the scale? I think it's clear from this simple plot. Yeah, it's this one, for example. You see the green.
I'm not sure, like all this resistant diagram work. It's like each point is like a subgraph of the original graph.
In a way, yeah. So you are building a filtration literally by drawing, by exploring your graph at the different scales. So it's like zooming out, basically.
So the connected component changes.
Yeah, exactly. So that's basically how it works, and you can look at the connected component, but also higher order interaction, like simplexes. And this is what you see in this graph. Like, for example, this point in blue here represents the bigger hole, like a cycle. Okay, this point up here. Then you had all these little cycles, which were the one in blue that you see underneath, like. And then in red, you have the edges. Okay, so if I'm cutting here, I'm basically getting rid of all these small edges and all these small cycles. And I'm just retaining 1, 2, 3, 4, 5, these, 6 edges. And I'll keep this big cycle in the middle because it's the most topologically relevant somehow information. And you're exactly picking a scale, you're cutting.
The joint component that exists.
If you have disconnected components.
But
No, it can work in theory also if you have disconnected components. The question is, do they develop at the same scale or not? But that's a good point. Like if you have two disconnected components and one has a very large scale, like for example, like very big branches, and the other has very small scale, then I might get rid of completely of one component because the scale is big. But potentially you can extend this and tune the different scales to different connected ones. But the theory works also to disconnect.
Yeah, it's very interesting work. I just wanted to naively, had I been faced with this problem, I probably would have just sampled some nodes and then do something like a random walk subsample construction.
Yeah.
And use that as a coarsening. So why would that not be so good?
Good point. I don't know, but you mean like I can randomly sample some nodes from the graph I already have, and then kind of see if like walk on these subgraphs that I built and see if it's retaining information, a good amount of information.
Yes, people do this random walk sampling so that they pick nodes and then they look at all the shortest paths between these nodes and include them as the edges. Right?
But how do you measure if you're retaining important information somehow?
Well, you look at whatever you're interested in, like clustering coefficient or
Okay.
spatial spread and see what it matches.
Yeah, I mean, that could be another idea. Yeah, probably. The reason why we wanted to look at them like this, I think it comes from the fact that we are looking at this object from a shape analysis perspective. So in a way, we wanted to really group the structure and really, being able to recreate the graph that is robust with respect to these main characteristics, but probably it might work as well. For sure, maybe it's more efficient computation, which is for now is one of the main problems of this. Okay.
Well, thank you so much.
Thank you for having me.
Screen.
Of course.
The references, please.
Of course. Oh,
This is put by Aaron.
he wants to.
I'm not sure about the pages.
Oh, yeah, just talking.